Welcome to the lecture number 25. So, let us continue our discussion on fluorescence quenching that we are doing for last few lectures, and we have already get some idea about the types of quenching. We got the idea of static quenching, dynamic quenching, combined static and dynamic quenching. Then we have seen the quenching sphere of action. So, in that case the apparent static quenching term is coming in, where we are getting a smaller value of Ks, which is because of the immediate presence of quencher next to the fluorophore. And then we have also seen the quenching resolved emission spectra. And now today I wanted to show you some application of this fluorescence quenching method. So, let us start with one by one. So, there are several things we can do with this fluorescence quenching method, like the characterization of protein, let us say. In this case, fluorescence quenching method is being used. For example, let me take a protein, right. I can just draw my protein like this way as usual, and there was a debate between two diffractionists. One diffractionist said that, okay, I have two tryptophan residue. As I told you, these tryptophan residues are kind of amino acid which are fluorescent in nature, right. So, one diffractionist said that I have two tryptophan residue, one is present at the surface and another is also present at the surface of this protein. And the second diffractionist come in and he told, no, my experimental results tells me that both the one of them are present at the surface and another is buried, right. And now what to do, right? But using your fluorescence quenching, you can resolve this. And suppose you are doing this quenching experiment. For the tryptophan, both are present at the surface, the quenching will be much more. Now, if the tryptophan, one of them is present in the buried location and another is exposed at the surface, then you are going to see a lesser amount of quenching, because the tryptophan which is present in the buried location will not contribute to the fluorescence quenching, right. I mean that quencher will not be able to reach that buried tryptophan and it will not be able to quench the tryptophan emission. So, the fluorescence intensity will not decrease that way that it would be for the case when both the tryptophan will be present at the surface, right. Okay. Number 2. So, you can also do this protein conformational change. You can also study by fluorescence quenching method. For example, suppose you have a protein, let us say this is your protein, and you have this tryptophan residing over here. Now, if you add a quencher molecule from outside, that quencher molecule will not be able to reach this tryptophan residue 100%. So, the fluorescence intensity of this tryptophan, which is the intrinsic fluorescence of this protein, will not going to be affected by addition of the quencher in the solution. Now, consider that you have done something on this protein, so that this protein chain, right, the secondary structure of the protein is getting distorted. That is what is referred as the unfolding of the protein or the change in the conformation of this protein, right. So, you do something, you put some perturbation so that the protein is unfolded. Now, as the protein is unfolded, right, the structure of the protein will change. Suppose you have this structure, and this structure as it is unfolding, the structure is getting changed like this way. Okay. So, that tryptophan which was originally here on the buried location, this is my TRP, it is now over here still again in the buried location. Now, it is opened somewhat and now it is fully open. This is my tryptophan residue. So, depending on the condition, depending on the secondary structure of this protein, the accessibility of this quencher will be different. So, in this case the quencher cannot interact with this tryptophan, here also it cannot interact with this tryptophan, but here somewhat it can interact with this tryptophan, and here the interaction with the tryptophan is quite easy. Now, it tells me that if I do this quenching experiment, here the quenching will be low, here also low, here moderate quenching, but here I will get high quenching of fluorescence. Now, consider that as you are giving this perturbation could be anything. This perturbation could be the raise in the temperature, this perturbation could be the adding of some foreign agents like guanidine hydrochloride, urea. These are the well known chemical denaturant which actually unfolds the protein. So, this perturbation could be anything. This perturbation also could be the lowering the pH. So, if you change the pH of the medium from neutral pH 7.4 to 2 or 1, then also this is also acts as a perturbation. So, the protein is getting denatured or unfolded. In this case, right, if the now if I plot the quenching, right, I can plot the Kd, right, because this is a typical dynamic quenching. So, if the Kd value is more, right, you remember here. So, when I plot I0 by I, then versus Q, I get a straight line with intercept equal to 1 and my slope is Kd, right. So, Kd more means the quenching is more. So, in this case I will get, for this case where the quenching is low, I will get a low value of Kd, then as I will go in this direction, then the Kd value will larger and larger. So, large value of Kd. So, now if I plot the observed Kd value as a function of this perturbation, right, if it is the temperature, then what I can simply do, I can simply plot the measured Kd value as a function of temperature. So, here temperature is my perturbation, it could be other thing also, right. So, then what I am going to see, the value of Kd value was really small, right, over here initial temperature or the temperature is lower. So, let us say here is my room temperature, and as I increase the temperature, so it may suddenly increase like this and then remain same, like such kind of feature, right. The feature is, it is almost similar here, then suddenly increase and then remain same, right. Such kind of feature, by looking at such kind of feature, you can comment that this unfolding of this protein when you raise the temperature is a two-step process, right. Here is your native state, in this part is your native state, and this part is your denatured or unfolded state. So, you see, by simply doing this quenching experiment, right, of such kind of molecule, you can comment on how the structure of protein is changing by increasing the temperature. Suppose you have done this exactly same experiment, but not temperature as your perturbation, but the change pH as your perturbation. So, in this case, let us assume that here you have used pH as your perturbation. So, and you have measured this Kd value at a different pH. And you are plotting it this versus pH, and what you have seen is that such kind of feature at neutral pH. Let us say here is my 7. At neutral pH, the value of Kd what you have observed from your experiment is really low value, right. And as and a little bit of higher pH 7.4, 7.6, 7.8, this value is like this. As you increase the pH, probably you have seen such kind of data, and the trend is like this. It clearly tells you that when your perturbation is this pH, here is your perturbation, then the change of Kd is 2 step. Here is a transition number 1 and here is your transition number 2. If I assign this, you can do so, no, assignment. If obviously the physiological pH is my native state, I assign this as native state, and if this is my denatured or unfolded state, I can clearly tell that I have some state which is not denatured, nor native, like intermediate state. So, I would have the signature of intermediate state in this case, right. So, in this case the denaturation is not a 2-step process, this is a 3-step process. So, I can write the native state of the protein is first changing to some stable intermediate state, and then this is converting to the unfolded state. So, this is a 3-state process. Okay. We can also study the protein drug interaction by this method. Number 4, which I will discuss in elaborately, is you can also use this fluorescence quenching for the determination of aggregation number of micelle. So, for the aggregation number of micelle, so let me first tell you that what is micelle. So, micelle is a supramolecular aggregate. Okay. So, this supramolecular aggregate is made of surfactant molecules. What is surfactant molecules? You have a long aliphatic chain with a charge head group, either positive or it could look something like this, negative. So, this is a charge head group, like the famous name of this surfactant is SDS, is sodium dodecyl sulfate. So, you see this sulfate, this is a negatively charged head group, and dodecyl, this is my alkyl chain, right. Similarly, CTAB, cetyl trimethyl ammonium bromide. So, here is my positive head group and here is the long chain, right. So, this is a positively charged surfactant head group, this is the negatively charged, and so on. So, if you keep on adding the surfactant in water, let us say in water, then after a certain concentration, these surfactants will form a supramolecular aggregate, right. Then after a certain concentration, these surfactants, right, will form a supramolecular aggregate. That looks something like this. For this surfactant, all the head groups of the surfactant will come outside, and this hydrocarbon chain of the surfactant will come together to form a kind of spherical structure. Is a kind of spherical structure as I have drawn over here. These are all the positively charged. So, this positively charged is exposed to the water, and this hydrocarbon part I am making a core like of thing. So, basically this part is like oil. So, this inside part is like a oil and the outside is water, and the outside is water. So, this is like a, I have a droplet of oils, but these are very tiny, right, in size is nanometer size, droplet, oil droplet in water. And because of these, actually the surfactants like our detergent actually helps to wash our clothes, right. Okay, that is a different story. Let us proceed. These surfactant molecules forms such kind of supramolecular aggregate only after a certain concentration, right. If you add this surfactant, let us say this is your water and you are keep on adding this surfactant, just for a very small concentration it will not form this micelle, only after a certain concentration those kind of micelles will form, like these balls like micelles will form, and that concentration is known as critical micelle concentration, and generally written as CMC. So, for this different surfactant has a different values of CMC. Like for this, as I said, this SDS, the CMC of SDS is 8 millimolar. So, after it cross the 8 millimolar concentration in water, then only such kind of micelles will form. On the other hand, for the CTAB, it is about 1 millimolar. So, after 1 millimolar, this CTAB will form such kind of micelles, right. Okay. Now, as I have drawn this figure, like it consists of several surfactant molecules. This is number 1, 2, 3 dot 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 n number of surfactant molecule actually makes this micelle. The question is how I am going to determine this CMC value and the aggregation number. So, for this micelle formation from the surfactant, I encounter two things. One is that critical micellar concentration, and after it the critical micellar concentration, n number of surfactant molecule will form this micelle, and that is called the aggregation number of this micelle, and that is called aggregation number and denoted as n AGG. Now, my question is that how we are going to experimentally determine this CMC and this n aggregation. So, there are several methods to determine for the determination of the CMC. For example, surface tension, the surface tension of the air water interface, right, will keep on increase as you add the surfactant, but after the CMC that will remain same. If you measure the molar conductance will be almost similar, right, before CMC, but once the surfactant will form the micelle, the molar conductance will decrease because of the bulky nature of this micelle. However, as we are doing the basic course on the fluorescence spectroscopy, we will try to tell you a method based on the fluorescence, right, how to determine the CMC and the n aggregation. For the measurement of the CMC, right, you see the situation. I have solution, let us say this is water, and let us take one fluorophore inside this water, right, with some concentration. Let us say these are my fluorophore, these are my fluorophore, and the structure of this fluorophore is, this is my fluorophore, and this looks something like this. Looks something like this. So, you see this is not a polar molecule, but there is a low solubility in water. So, the solubility of this molecule is higher in non-polar medium than in the polar medium. Now, you are keep on adding this surfactant molecule, let us say these are your surfactant molecule. So, you are keep on adding. So, surfactant molecules are there. As you increase the concentration of the surfactant molecule is keep on increasing, and there is not much change in the local environment of this fluorophore. In this case, if I now plot the fluorescence spectra of this molecule, how you will get? You just excite with a suitable light, lambda excitation, and then measure the fluorescence intensity as a function of wavelength, then you will get the fluorescence spectra. So, I will just plot intensity versus lambda emission. So, you will get the fluorescence spectra of this molecule. Let us say the fluorescence spectra looks something like this. Now, you are not changing the number of molecules in this medium. So, it remains same because you are not adding more number of this fluorophore. You are not adding more number of fluorophore with time. So, the number is remains same. What you are adding is the surfactant. So, the fluorescence intensity will not change that way, right. Okay. Now, as you are adding the surfactant, you keep on measure the fluorescence spectra of this molecule. So, when there is no surfactant, let us say it looks like this, no surfactant, and as you are adding surfactant, you are measuring. Initially, there is no change, it will remain like this, remain like this, remain like this. But once there is a formation of those micelles, when it will be? Once the concentration of the surfactant will cross or will reach the CMC value. So, then there will be formation of supramolecular aggregates of the surfactant molecules, and automatically as these fluorophores likes to stay in oil. So, then this fluorophore will go inside these micelles, because inside the micelle, as I said, is oil like, outside is water. So, it will prefer to go inside the micelle, right. So, it will go inside. Once it will go inside, it will not going to see that much of water inside it. So, that inside the micelle there is no water, it is like a oil hydrocarbon. So, when you will going to excite this fluorophore, in the excited state will not going to be stabilized in the same way that it was in case of water, right. When it was present in the water, then the stabilization of the excited state was quite large because of the high polarity of the water, but inside this micellar environment the polarity is low. So, it will not going to stabilize. So, what we will going to see? You will see a sudden change of emission maxima. Why? Because the emission maxima tells me that how much it is solvated. If it is solvated more, the same as the Lippert-Mataka, right. When you increase, this is the case of excited state dipole moment is more than the ground state dipole moment. So, here you see there is a change, and when all the fluorophores will be inside, then there will be not much change in the shape of the emission spectra. So, if I now plot in a different way the concentration of surfactant versus lambda emission maximum, then for the low value of the surfactant, right, this lambda was the high value, right, lower energy as you have seen here. So, you will get such kind of thing, and then it will, once there is a formation of these micelles, this value will decrease, and then it will be again constant. So, from here what you can get, the midpoint is nothing but the value of this CMC. We can use this fluorescence quenching now to get this aggregation number of this micelle. Now, let us see how we can use this fluorescence quenching to find out the aggregation number, right. Like we have found the CMC value by fluorescence method, but in this case we will use the fluorescence quenching method to find the aggregation number of this micelle. We will find the n aggregate. Okay, let me define all the terms step by step, and then it will be very easy for you to understand. So, here first term I am going to define is, let us say, the concentration of surfactant. Let me use this symbol S to denote this aggregation number let us say N AGG, as I said earlier. Concentration of quencher, let us denote it as Q as usual. That critical micellar concentration, that is my CMC. Now, I can write from here the concentration of micelle, or I can write here concentration of micelles. This will be equal to, let us represent this as M, this is equal to concentration of surfactant minus that CMC value, because only after CMC the surfactant will form the micelle, and divided by aggregation number, that means N AGG, right. And I can now also try to define this quantity, that number of quencher molecule per micelle, right, represented by this average Q. This is nothing but the concentration of Q, concentration of the quencher divided by the concentration of micelle, and that will going to be the average. It is not necessarily that all these micelle will have that exact number of quencher, but that is my average, right. So, I will just simply write here concentration of Q divided by this M, right, and I know how to write this probability. So, let me write that the probability that a particular micelle having the same way earlier I have done, right, having n quencher molecule, that using my Poisson distribution I can write P n. This is my average Q, right, to the power n factorial n e to the power minus average Q, right. Now, I will take two assumptions which are obviously valid assumptions, right. Let us take these assumptions with this other color. Here the first one I will take as the fluorophores and quenchers are such that the both can be present in the micelle. It is not that the fluorophore is completely hydrophilic, it is a charge, and micellar surface is positively charged, fluorophore is also positively charged. So, fluorophore will never come to the micelle. I will not take such kind of situation. I will take a neutral molecule, neutral fluorophore, neutral quencher, so that it has a hydrophobic part, hydrophobic interaction is favorable. In that case, those fluorophores and quencher will go and sit in the micelle. So, that depends on me. I can choose the type of fluorophore and quencher which will go and sit on the micelle. It will not remain in the solution, right. So, the first assumption, which is a valid assumption, I will write here both the fluorophore and the quencher stay in the micelle, and the second one is that even I have a single quencher present in the micelle, that is good enough to quench the fluorescence completely of the fluorophore which is present in the micelle. Clear? Okay. So, even a single quencher will deactivate all the fluorophores in the micelle. In this case, I will not create such kind of situation at all. I will use the fluorophore concentration is low, so that each micelle probably will have on an average less than 1. It means that some micelle will have fluorophore, some are not, right, but I will use the quencher more. That means, the micelle which are having fluorophore, that must contain a quencher. I will create the condition like that way, right, and there is a very little chance that a micelle is having more than one fluorophore, but only one quencher. That condition I will not let it come, right. So, in this case both will be satisfied. If so, then let us see what will happen. So, then I can write the probability that a micelle having no quencher, that is simply P 0, which is q, that average q to the power 0 by factorial 0 e to the power minus this average q, which is nothing but e to the power minus this average q, right. So, here this means, right, I can write I by I 0 is equal to e to the power minus q, right. This means this. So, this is equal to e to the power minus q by m, which is equal to e to the power minus q n aggregation, because I know this means that, right, s minus that CMC value, whatever it is. So, if I take ln, so ln I 0 by I is equal to q n aggregation divided by s minus CMC, right. Now, I can make a plot easily. So, the plot I will do like this way. I will plot ln, this is measured quantity, right, I 0 and I, they are measured quantity. I 0 is the fluorescence intensity without quencher and I is with quencher. So, I can take the ln of that and I plot the ln I 0 by I versus q. So, then this should be a straight line passing through the origin. So, then this should be a straight line passing through the origin and the slope would be in AGG divided by concentration of the surfactant minus the CMC value. I know this concentration of the surfactant, right, for a particular experiment, and the slope is known. CMC you already have determined from other experiment. So, you can simply get the n aggregation value. So, you see that using fluorescence quenching easily we can determine the n aggregation value. Okay. So, we will finish here and thank you for listening.